As we saw in the last video, there are two ways in which you can make connections and connect loads in three-phase system. We learned about star connection in the last video. Now let us learn about delta connection. Let us consider the individual or isolated coil arrangement again. In star connection, we had replaced one of the conductors from all the coils by a common conductor. In delta connection, we do it in a different way. The intention remains the same, that is, to reduce the number of conductors and hence the costs associated with it. In delta connection, the finishing end of one coil is connected to the starting end of the next coil. So, we are replacing the two conductors 2 and 3 with a single common conductor. And we also replace the conductors 4 and 5 with a single common conductor. But before we connect the finishing conductor B' to the start of conductor R, we need to prove that the resultant EMF between these 2 points is 0 at every instant. It will ensure that no circulating current is set up when these 2 conductors are connected together. It can be proved very easily. The instantaneous value of the total EMF from B' to R is ER plus EY plus EB, which is equal to EM sin omega t plus sin omega t minus 120 plus sin omega t minus 240. On simplifying this equation, we get the value as 0. As this condition holds for every instant, we can join R and B' together without creating any circulating current in the circuit. This delta connection can be represented in a better way like this. The three-phase load or single-phase load can be connected across this connection. As we saw in the star connection, individual phases can be connected to device or all the three phases can be used together depending on the device and requirement. Now let us look at the line and phase voltages. The phase voltages in delta connection are like this. We have E12, the voltage between terminals 1 and 2, E23, the voltage between the terminals 2 and 3, E31, the voltage between terminals 3 and 1. The current flows in the same direction as well. These are the phase voltages. Coming to the line voltage, we have ERY, the voltage between the line R and Y, EYB, the voltage between the line Y and B, and EBR, the line voltage between the lines B and R. If we observe the relationship between phase and line voltage here, the voltage across the terminals 1 and 2 is the same as across the terminals R and Y. That is, E12 is equal to ERY. Similarly, we have E23 is equal to EYB, and finally E31 is equal to EBR. So it clearly tells us that phase voltages are equal to line voltages. In delta connection, line voltage EL is equal to phase voltage EPH, but the relationship between the phase currents and the line currents are a bit different. The line current IL is equal to √3 times that of the phase current IPH. You can prove these relationships mathematically in many different methods, but understanding the line and phase voltages and currents are the key. This is all about delta connections in three-phase system. To sum up, we learnt about the conductor connections. We also learned that the line voltage is equal to phase voltage and line current is equal to √3 times the phase current. In the next video, we learn about measurement of power in three-phase circuits. See you there.